Calculating limits using algebra. There are many different methods that you might have to use when calculating a limit, and it's just going to depend on what type of expression you're having to take the limit of. So let's just do a quick example of most of the different ones that you might see. The first method you should always try for calculating a limit is just direct substitution. So for example, if we have the limit as x approaches 3 of x squared, direct substitution is simply plugging the number that x is approaching into the function or expression. So in this case we would get 3 squared, and the answer, the value of the limit, is 9. So as long as you get an actual number when you substitute, then direct substitution will work, and you have your answer for the limit. Okay, with this example, when we try direct substitution and just plug the -1 into the x's, we would get 1 minus 3 plus 2 on the top for the numerator there, and we would get 0 in the denominator. And then we would see 1 minus 3 plus 2, well, that's also 0. So plugging in the value -1 gives us this fraction 0 over 0, and this is what is known as an indeterminate form. So this is something kind of special. It basically means that this limit should have an answer, but we haven't found it yet. And there are several different indeterminate forms. 0 over 0 is very common. So is infinity over infinity. You also may see infinity minus infinity, and 0 times infinity. There's some other ones too, but these should be enough for now. So if when you're doing direct substitution you end up with one of these indeterminate forms, then you know you're going to have to continue on and do some other method in order to find the value of the limit. And when you're doing the direct substitution, if you end up with a number divided by 0, 1 over 0, we know that's undefined, but this actually approaches infinity, so this would count as infinity. And if you have one or any number over infinity, that's going to approach 0, so that would count as 0 for your indeterminate forms here. So what do we do in this case since it is indeterminate? Well, we have polynomials here, so we would try to factor these and see if we can cancel this common factor, which is kind of causing this indeterminate form here. So if we look at our numerator there, it looks like we should be able to factor that. X plus 2, x plus 1 should do it. And we see that we have a common factor of x plus 1 in the numerator and denominator, so you probably have done problems like this where we can cancel this now, but it's important to point out that we really are only allowed to cancel these if x does not equal -1. If x were to equal -1, then canceling these would be dividing by 0, which you cannot do. But since x is merely approaching -1, it's not actually equal to -1, then it's okay to cancel these. And so this limit would simplify to the limit as x approaches -1 of just x plus 2. Now we can substitute again the -1 in for the x, and we don't have a problem this time. We just get our answer of 1. Okay, so this example here has this radical here, the square root of x, and if we try direct substitution, we would get the square root of 4, so 2 minus 2 over 4 minus 4, which is another 0 over 0 indeterminate form. So we could continue on here, and when you have these square roots, these radicals, the method you want to use is rationalizing. So we're going to multiply by the conjugate over itself, or multiply both the numerator and the denominator by the conjugate of this part here that has the radical. Sometimes it's in the denominator, sometimes the numerator. In this case it's up here. So we're going to multiply by the square root of x plus 2 over the square root of x plus 2. And really this is just equal to 1, so that's how we're able to multiply it, because we're not really changing anything, we're just multiplying times 1. And now multiplying out the numerator there with those conjugates, this is a sum and a difference, so we can multiply that shortcut and get a difference of squares. So that's going to be x minus 4. And then in the denominator, we're actually not going to multiply those out. We want to leave them as two separate factors here so that we can cancel. this common factor. We have an x minus 4 that'll cancel, and since x is approaching 4 but not equal to 4, we're allowed to cancel that. So this limit now becomes the limit as x approaches 4 of just 1 over the square root of x plus 2. And now we can plug our 4 into the x here, and we get 1 over 2 plus 2, or 1/4. Okay, this example has these two rational expressions that are being subtracted. If we try the direct substitution and let x equal 2, then this would be 1 over 0 here, and this one would also be 4 minus 4 down here would be 1 over 0. And remember, when you're looking at indeterminate forms, number over 0 is going to approach infinity. So this is an infinity minus infinity indeterminate form. So the method we want to use when we have rational expressions like this is to get this common denominator here and combine these or subtract these two fractions into one fraction, and then we should be able to cancel that common factor. So the first thing we need to do, if you remember back to pre-calculus or advanced algebra, is you'd factor these denominators here so we can find the greatest common factor there and get a common denominator. So let's do that first. And we can factor out a 2 from this one, and then we can factor out the x on this one here. So looking at our two denominators, they both have a factor of x minus 2, but this one has a 2 and this one has an x. So we're going to need to multiply this first fraction by x over x and the second one by 2 over 2. So after multiplying by those missing factors, we have a common denominators. We can now subtract the fractions. And now you can see we have this common factor of x minus 2. And since x is approaching 2, not necessarily equal to 2, we can cancel those out. And we have the limit as x approaches 2 of 1 over 2x. Now we can substitute the 2 in for the x, and we get an answer of 1/4. With this example here, we have some trigonometric functions, and if we try to do our substitution here, we have the sine of 0 times the cotangent of 0. So the sine of 0 is equal to 0. But the cotangent of 0, cotangent has a vertical asymptote at x equals 0, so cotangent here is going to be approaching infinity, and this would give us a 0 times infinity, which is one of the indeterminate forms. So when you have a limit with some trigonometric functions in indeterminate form, what we'd want to normally do is use some trig identities to rewrite this expression and see if we can cancel a common factor. So one easy identity we might use is to rewrite the cotangent of x as cosine of x over sine of x. So let's try that. And now we can see we have our common factor of sine that we can cancel out, and this gives us the limit as x approaches 0 of just the cosine of x. And doing the direct substitution, we get the cosine of 0, which equals 1. In this final example, we have a piecewise function, and we're asked to find the limit here as x approaches 2, which happens to be the value where this piecewise function switches from one equation to the other one. So in these cases, we need to check both sides of the limit separately, the left-hand side and the right-hand side, and see, because in order for this two-sided limit here to exist, the left and right side would both have to equal the same thing. So first let's check the left side as x approaches 2 from the left of our function. And so if we're approaching 2 from the left, we're going to be at values which are smaller than 2. So we want to look where x is less than 2. And here we have x plus 3. So we would just substitute the 2 in for the x here. So this left-hand side, we would find that the limit is 2 plus 3, or 5. And then we would check the right-hand side, so x is approaching 2 from the right, which means that we are at values that are larger than 2, x greater than 2, approaching, so we're using this equation, and we just substitute the 2 in for the x there. It gives us 2 squared plus 1, which also equals 5. So since the left and the right hand side both equal 5, we can conclude that our two-sided limit here equals 5 as well.